understand that our 100-watt control module, that module that we call it simply as the DR100-watt CM with this block diagram. The center of the block diagram is the microcontroller unit. I simply call it here as a MCU for short, and the MCU refers to the Intel 8051 core MCU. When I say Intel 8051 core, I'm referring to the Atmel 8089S52 MCU, or to the STC 90C516RD Plus MCU. So these are the two 8051 core MCU that I have used in this project. Let's see the first hardware that is interfaced into the MCU. This is the 20x4 LCD. It is interfaced to the MCU with the data bus and control bus. The data bus is composed of 4-bit data lines. The hardware team make use of the 4-bit data line instead of the 8-bit data, so that we can save some MCU ports. The control bus composed of EN and the RS. The 20x4 LCD comes with a backlight, and we need to control the backlight as well when we want to turn on the backlight and turn off the backlight. What we want to do is that when the system is not being used, then we want to put the backlight into the sleep mode by controlling the backlight control to turn off the backlight. In that way, the power consumption will greatly reduce. The second circuit that is interfaced to the MCU is the DR100W PA module. PA means power amplifier. Again, we need to control the PA so that we can manage it. In terms of power management, we can put the PA into the sleep mode so that it will reduce the power consumption. Now, the PA comes with 3 control points. The first one is the standby mode. The second one is the speaker mute. And the third one is the speaker protector. So, as I mentioned, the standby mode is used to control the PA to put into the sleep mode. The speaker mute is used to suppress any noises that is being generated internally during the power on and power off stage of the PA, so that we will not be hearing this kind of noise into the speaker. And the speaker protector is put it into the DR100W PA module to protect the speaker from dangerous offset voltage. You know, the speaker is a very expensive audio stuff, so we need to protect it from possible damage. The next circuit that is interfaced to the MCU is the EEPROM. So why we need an EEPROM here if we have the MCU already? There are several MCU that do not have the EEPROM internally. So the STC MCU don't comes an EEPROM internally, so we have to use an external EEPROM circuit. So basically this is an IC, and the purpose of the EEPROMs is to save the user last setting data. So what is meant by that? For example, the user set the volume control to 25 dB, for example. So the MCU will save the 25 dB data into the EEPROM. The reason why we need to do that is that when we are going to power off the whole system, it means to say that we are going to remove the DC supply, then all the data in the MCU will be erased, or it will be lost. Now the EEPROM will hold the data. Even we will turn off the power of the whole system, it will keep the data, so that when we turn on the system in the next usage, then we can read the 25 dB data from the EEPROM, and then the MCU will going to use it. So that's basically the main purpose of the EEPROM. And the communication between the EEPROM and the MCU is what we call the I2C communication. I2C means inter-IC communications. So this is basically a protocol of devices that is talking to each other. The I2C also is being used in the dr100w EQ. This is another module. The EQ means equalizer. So in this module, there is a tone control IC, which is also being controlled using I2C protocol. So if we wanted to increase the volume, then we command the tone control IC to increase the volume by means of I2C protocol. The dr100w EQ module is also controlled by this MCU port, which is labeled as SPI or P1. But in here, we are not using the SPI. SPI means Serial Peripheral Interface. So this is another communications protocol between different circuit blocks. In here, the SPI ports is being used only as TTL, or the transistor logic, controlling logic 1 or logic 0. So there is another chipset in the EQ module, which is responsible for the equalization, and we are controlling this EQ chipset by means of logic 0 or logic 1, or combinations of logic 1 and logic 0. So in short, the dr100w EQ being accessed with the I2C protocol, and then we also access the dr100w EQ module with logic 1 and logic 0. The real SPI control is on the programming the MCU. So when we are using the Atmel 8051 core MCU, when we want to burn our hex code into the ROM of the MCU, then we are going to make use of the SPI communications. So what we going to do in here is that we will have here an SPI socket where we put the USB bridge, and then we have flash programmable application software into the computer, and then we send the hex code and burn it into the ROM of the MCU. So that is the way we program the Atmel 8051 core MCU by means of SPI communication. Now there is another programming here for the MCU, which is dedicated for the STC MCU. So we program this STC MCU by means of the UART and not by SPI. So we have here a USB TTL module, or we call it the USB bridge. It is a bridge because this is the hardware that is interfacing the MCU and then the PC. So this USB TTL module will plug in into the USB port of the PC, and then we have an application software on the PC which is called the ISP software that will drive the system to burn the hex code into the ROM of the MCU. So that's a pretty simple and cost effective by programming the MCU using the UART port. The UART means Universal Asynchronous Receiver Transmitter. Is another communications protocol. Let me jump to the RF RX module. So the function of the RF RX module is to remotely control the system, especially the DR100W CM module. What's meant by remotely is that say for example we are just about 10 meters away from the amplifier, and then we want to access the volume control to increase it or lower down the volume control. Then we can make use of the radio frequency, and by RF RX module and the equivalent RF transmitter to increase the volume. So how we do that is that the RF system, which is operate in the 315 megahertz, or it could be also in the 433 megahertz, will have an RFTX, or the radio frequency transmitter. So we have some button here where we can designate for the volume up, volume down, tone control, bass, treble, and other function, so that when we press any of the keys here, it will send code to the RF RX module, and then it will receive it and then send data to the MCU. So we have here 4-bit data composed of like DO, D1, D2, and D3, and they are in parallel and interface to the MCU. So when we send the signal here and then received by the RF module, this 4-bit data will have a logic level, either 0 or 1, and or combinations of 0 and 1, and then the MCU will going to read this 4-bit data and interpret the logic 0 and 1. So that's pretty simple, and the programming is pretty easy as well. So that's just one way on how we are going to control the DR100W project remotely. Let's see the keyboard or the keys. Our project, DR100W concept, is a power amplifier, and we have a means to communicate to the user by means of the keyboard. So for example, the user want to increase the volume or decrease the volume. All what you have to do is to press the volume up or the volume down. So basically the keyboard is the man-machine interface. We have 5 keys. The first one is the power on off keys, the menu, select, up and down keys, where they were mentioned that way because of the mode of operations, like when we say menu, select, and up and down means to say that the mode of operation at that time is programming. So for example, we wanted to set the time, then we need to go to the menu and then set the correct time and hour, I mean the hour and the minutes. But when it is in the amplifier mode, it's out of the programming. That means these keys can be selected to change the equalizer, the volume, the tone control, bass, and treble. So this keys function is dependent on the mode of operation. So what about the buzzer? Alright, the buzzer is basically another communications to the user by emitting a beep. Well, we know that when we play our mobile phone, when we press the keys, then we can hear a beep, maybe the DTMF beep. So that kind of beep will basically interact with the users when he will press any key, and then he will hear the beep. It means to say that the pressing of keys is successful. So we included the buzzer here as a means of communication to the user. And of course, the system needs the power supply, which is plus 5 volts at the BCC. The plus 5 volt is normal to most of the microcontroller. So what we have here is that the control module has its own power supply. So we have here an input of plus 12 volt DC, or we can have it also as a 9 volt AC, and then it is rectified and filtered by the power supply. I think we are using here a passive regulator, which is the LM7806, and then we drop down to plus 5 volts here, going into the microcontroller. And we have here also an indicator, an LED indicator. That the purpose of this indicator is that when we power on the system, and this LED, as controlled by the software, will blink or STD or something that indicate that the microcontroller is turned on and it is working functionally. Let's see the crystal and reset. Well, the crystal and reset are basically standard for microcontroller. The crystal is a mandatory requirement, which is an external source. So most MCU requires an external source for the clocking. And the reset is an external circuit, or it could be an internal circuit as well, for newly invented 8051 core MCU. So the reset will properly set the internal registers and processing of the MCU. This is basically an RC circuit. For the Atmel 8089S52 MCU, it requires an external reset. But for other MCU, which is a newly designed MCU by STC, the reset is included internally, so that the external reset is no longer needed. This circuit block here that enclosed with the dotted lines is the optional hardware. So I put it here on optional, since these hardware modules like the Bluetooth module and the touchless volume control, and of course the infrared receiver transmitter may not be in this current project, but it is intended for future application for anyone who would like to play around with the Bluetooth, the infrared receivers, and as well as the touchless volume control. Let's see about the Bluetooth module, or the BT module. Nowadays, the BT module is a very popular interface, and what is pretty simple about this one is about the how it is interfaced with the MCU, which is make use of the UART communication. The idea is that if you want to control the control module or the whole system dr100w concept project by means of our mobile phone, then we can make use of the BT modules. We included the traditional infrared remote control, where you have to point this remote control to the IR sensor so you can control it. the BT module and the RF RX module, you don't have to point the transmitter or the controlling device to the dr100w concept module in order for you to control it, but you must be within the RF communication range to control it. So what's this about the touchless volume control? So I mentioned here in the keyboard that we have the keys for volume up and also keys for volume down, and these keys, you need to touch the keys or you need to depress the keys to execute the volume up and also volume down. But in here, the touchless, as its name implies, you don't have to touch the keys in here, but what you have to do in here is that you have to put your finger or put your palm near the sensors, and basically you can increase the volume and also decrease the volume. So there will be two sensors here. So one is a volume up and another one is a volume down, which is a touchless. Well, more on that on the circuit explanation. And the last one that I am going to present is about the microcontroller GND, or the ground. Why I put it here is it's quite important, especially if you have a system like the dr100w concept, where we have two kinds of grounding system. The first one is the analog, and the second one is the digital. So the analog is grounding system employed in the dr100w EQ module, and the second one is the digital ground, which is being employed here and being used by the MCU. So when you combine these two kinds of ground, then this ground, if not were taken properly, will cause some kind of noise or interference to the analog portion of the circuit. That is why I have put in here, included in the block diagram, because in managing the whole system, there is a need to take care of the digital ground, which by experience we experience that the digital ground cause interference to the analog portion of the circuit.